Okay, we're back and we are still looking at sections 1.6 and 1.7. We're looking at normal stress and shear stress, and we're looking at factors of safety like we did in the last problem. We're going to be looking at an LRFD style problem next. And so there's two examples on this page because they're pretty short. So we're just going to do both examples 2 and 3. Okay, so we have tie rods A, B, and C, D are made of steel. Perfect, they're both the same. Determine the smallest diameter so that they can support the dead loads shown. The beam is assumed to be a pin connected at A and C. Use the LRFD method where the resistance factor for steel and tension. So, when we're doing different designs, we have resistant factors. Remember, that's going to decrease the yield stress, the allowable stress, whatever you want to call it, for the material. And for steel and tension, it's 0.9. It could have said, if we had a system that had steel in both tension and compression, we could have said that our compression would be 0.85. Okay, so we could have different values of phi depending on the type of application in our system. So tension, it's 0.9. The dead load factor is 1.4. The failure stress is given as 345 megapascals. So I know that my failure stress is given as 345 megapascals. And you all know me, I don't like to have to worry about units. So I'm just going to go ahead and put that in pascals. So a mega is 10 to the 6th, and I know that a pascal equals Newton per meter squared. And that way I can make sure I have the correct units in my equation. So in order to design A, B, and C, D, okay, I know they're made of steel. So I'm given the stress, and I want to know what is the diameter. So if I'm looking at an equation, stress is that normal force over area. I know it's normal force because they are going to be in tension as I push down. I was given that, and I'm going to have to reduce it. And I'm trying to find area, so I must be given then that internal normal force. How do I find it? Free body diagram. Always start with statics. If you don't know where to start with a free body diagram. So I'm going to have a normal in AB, a normal force in AB, a normal force in CD, because I know they're in tension, so it's strictly that internal. Again, we could have normal, we could have shear, we could have bending moment, we could have torsion, but right now with the loading, we know that all we have is that normal force because it's a tension member. It's a two-force member. Two force ends, it's just in tension or compression, so tension. And then I have 4 kilonewtons. I have 6 kilonewtons. I have 5 kilonewtons. Okay, and it tells me, what does it tell me about our loads? It tells me that we're going to be factoring our loads that are dead loads by 1.4. And we're not considering live loads. We're not even considering the weight of this. They didn't give us the dimensions to consider the weights. So how do I do this? Well, because these are all dead loads and they are all going to have the same factor, I'm just going to find the normal force based on these and then increase it by 1.4. If I were to have live loads as well, I might have to actually change the loads within my system depending on the factor that they have. But because they're all the same, 1.4, I'm just going to go with this. So we're going to sum our moments about A equals 0. And when I do that, I'm going to find that normal force in NCD is 6.7 kilonewtons. Then I'm going to sum my moments about C. And I'm going to find the normal force in AB is 8.3 kilonewtons. And I'm going to stop and look at my system. Does it make sense that AB is larger than CD in terms of normal force? Well, I do have a 5 over here, but the 6 and the 4 are much closer to this side than that side, so it makes sense that this has more force in it, okay? I could sum forces in the y direction to make sure, though, that I got it right. So now if I'm going to look at these internal normals that I'm factoring, remember I'm going to factor them. So I have my stress equals N over A. So let's look at rod AB. Stress equals N over A. Well, I'm going to be reducing my stress 0.9 times 345 times 10 to the 6th Newton per meter squared equals, okay, well, I know the actual force in AB, it's 8.3 kilonewtons, so 8.3 times 10 to the 3rd newtons, because I want everything in newtons and meters. And what am I doing with that? I'm actually increasing that by 1.4. And then the area, pi over 4, diameter of AB squared. And when I get this diameter, okay, when I get this diameter, it's going to be in units of meters. So I get the diameter of AB, and that equals 0.0069 meters. Well, that's a weird, I wouldn't go into Lowe's and ask for a diameter in 0.0069 meters. So area of AB equals 6.9 millimeters. That seems more reasonable. Okay, and then I'm going to do the same thing for this other rod. So I have rod CD, and it's in normal stress, N over A. So I have 0.9 times 345 times 10 to the 6th newtons per meter squared equals, and we had this load of 6.76 times 10 to the 3rd newtons, because it was in kilonewtons. And I have to multiply this by 1.4 because it's dead load, divided by pi over 4 diameter of CD squared. When I multiply this out, the diameter of CD is 0.0062 meters. So the diameter of CD is doink, 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 6.2 millimeters. So a couple of things. When you're finding these internal normal forces and you're finding areas, you really, really need to make sure that you're distinguishing the normal force of CD, the normal force of AB, the normal stress of AB, because you may end up with several different tie rods in a system. And they may all have different diameters. They may all have different allowable stresses if they're different materials. And so you need to keep up with making sure that you signify what you're working with. Otherwise, you could possibly end up with wrong answers. The other thing is I may not be able to go into Lowe's, say, and order a 6.2 millimeter rod. They may only come in whole unit dimensions. 1 millimeter, 2 millimeter, 3 millimeter, 4 millimeter, 5 millimeter, 6 millimeter. So if I need a 6.2 millimeter rod, it seems like, well, if I'm rounding, 6 millimeters is closer in terms of rounding, but this is the minimum diameter I need. So if I were actually looking for to the whole number, I would have to say that that tie rod needs to be 7 millimeters in diameter, because this is the absolute minimum it can be. This is the minimum it can be. I cannot round down. I have to round up to the next one. So if it said the minimum, the smallest diameter to the nearest whole number, then my answers here would be 7 millimeters, which is kind of easy to see. I mean, yeah, and then 7 millimeters, because again, we have to round larger. Okay, so this one is a bearing stress by the pin on the back of a hole. So if you have a hole and you have it fitted with a bolt, and you end up pulling on like that, this metal bar, and depending on the materials and the load, you could end up skewing that hole. And you guys have all seen holes that have ended up skewed, and they're no longer round. They're harder to get the bolts in and out of, but you could also end up with play in this connection that you are not counting on. Okay, and so let's calculate then that bearing stress. So the rectangular bar is connected to the support bracket with a circular pin. The bar width, so this direction right here, see that direction? The tall direction is 1.75 inches. The bar thickness, so that would be into the page that we can't see, is 0.375 inches. And so that goes back like that. And here's the bolt. There's an applied load P, and we can see it's axial of 5,600 pounds. So we are looking at a normal force. Determine the average bearing stress produced by the bar on the 0.625 inch diameter pin. So this pin right here, so we're going to kind of blow this up. See if I can do this. So if I'm looking back here, okay, well, hold on. Here is the pin, and it has a diameter of 0.625 inches, 0.625 inch diameter, okay? So when we're looking at the back of this wood, the bearing is going to happen right here at the back. See, right at the back as I pull, that's going to be the bearing. And so if I'm coming down here, I'm pulling, okay, at 5,600 pounds. And when I look at the bearing, so it's going to be the diameter, and then times that thickness of the wood. So I have this dimension here, and then into the wood is what's going to be bearing. So it's a normal stress because it's pushing. Okay, you see it's pushing. It's the back of the bolt pushing on the wood. So if we're pushing or pulling, it's normal. Normal stress from bearing equals, okay, that normal force that's being pulled by the cross section. So our stress then, our bearing stress equals 5,600 pounds divided by area. 0.625 inches, that's the diameter of the bolt, times 0.375 inches, that is the thickness. Okay, so that's going to be that cross-sectional area right there that's getting smushed, that the bolt is pressing on. And when I multiply this out, then I didn't actually multiply it out because I don't know why. Get my calculator out. And because my real calculator is batteries are dead. So I have 5,600 divided by 0.625 equals divided by 0.37. 5,600 divided by 0.625 divided by 0.375 equals, okay, that is a number that's in pounds per inches squared. So that's a huge number. So we're going to round this to 23.9 KSI. KSI. So 23.9 KSI. I'm still going to keep the inches on the bottom, but that pounds gives us a very large number. See that? So I'm just going to divide it by 1,000 and call it a kip, because a kip is a 10 to the third concerning pounds. So we kind of try to do a metric thing there. Okay, that's it.